Let us now discuss the referential method and more specifically the voltage scaling type. So we know this block diagram topology. You have the PV cell connected to the DC-DC converter. You have a capacitor buffer at the terminals of the PV cell, and then the load R0. So this is the DC-DC converter, and we have the terminal voltage Vt and terminal current It as shown like this. Then you have a control input D and R0. Let me draw the Vt versus It curve. This is the IV curve and this is the PV curve. Now the maximum power point is occurring somewhere here in this region. So if the insulation varies, there is variation in the IV characteristic. You will see that the IV characteristic changes, but the maximum power curve also will change. The maximum power point value also will change, but it will be within a certain band. It will be within a certain band like this, and we can say more or less within this band the maximum power operating point will lie in this zone. So we will call this as the VOC point, and we'll call this as the VM, the maximum power voltage. So as a approximate solution, we could say that if I choose Vt, the panel voltage, to lie always within this band, which means if I am having a load line which is in this band here, if I have load lines in that band, then more or less it is hovering around the maximum power point. It may not exactly be at the maximum power point, but it will be near around at the maximum power point, which is still very satisfactory in many of the applications. So literature has taken this approach that we make an engineering approximation, we make an assumption saying that Vm by VOC, that is this value divided by VOC value on the voltage axis, is a constant. And let us say approximately, if you say VOC is 100%, VM is at around 70% point, 70 to 90% point, but it will vary depending on the characteristic. Once you choose a particular PV panel from the data sheet, you can arrive at what this constant value is. Let us say it is around 0.7. So once you have made this assumption, now this becomes the rule. Given that panel and whatever may be the load or not, I will adjust the duty cycle such that the load line as seen from the PV panel will pass through in this range of slopes, and thereby the operating point when a vertical is dropped down onto the power curve will be more or less on the flat top near the top of the hill, and you can say near close to maximum power transfer is happening. So this assumption is the basis for this voltage scaling method. Now let us see how we go about realizing this voltage scaling method. So to this PV system interfaced with a DC-DC converter having DS control input, let us see how we will give the control signals for this duty cycle input of the DC-DC converter to achieve maximum power point transfer using the referential voltage scaling method. Now let us understand the control block schema. Now there needs to be a reference. Now this reference has to be compared with a feedback signal. So in any control system topology, you will have a reference signal and a feedback signal, plus and minus, and there will be an error signal. Now, for now, I am not going to tell what is this reference signal and what is the feedback signal. We will come to that later. But this error signal, what you have here, I can process that. I will process it through a controller. And one of the most robust controllers is the PI controller, proportional integral controller. So I will use a proportional integral controller. The output of the PI controller, this will be a DC value. Now this has to be converted to time in order to get duty cycle signals. So we need to do a pulse width modulation. So depending upon the DC value, there needs to be a voltage to time conversion. So that involves a comparator like this, and to this comparator, another input, we will give the carrier signal at triangular carrier. So when the DC signal and the triangular carrier are compared, the output of the comparator would be a pulse width modulated signal, and that output is what is given to the D input. The D input internally will drive the power semiconductor switch within the DC-DC converter. So this would be the schema. Now we need to see how what are the values that you need to give and what variable you would want to give here. Now let us go back to the voltage scaling rule which we just now discussed. The rule is, we made an assumption that Vm by Voc is set equal to a constant K, or Vm. Vm is the voltage of the PV panel at maximum power point or peak power point. So Vm is equal to K times Voc. So we now have a relationship of the maximum power point with respect to Voc and a constant. Voc is the open circuit voltage. Now what is the objective? What is it that we want to achieve from this block schema? What we want to do is that the voltage Vt, which is across the terminals of the PV panel, should be set equal to, so if I go to this IV characteristic, the voltage Vt should be hovering in this band. If it is hovering in this band, then the operating point is somewhere here, and what is the power drawn from the PV panel? It will be hovering around this region, so it will be close to the peak power point. So we need to see that Vm is as close to Vt, the terminal voltage across the panel, is as close to the Vm value as possible. Vm value we know in terms of Voc. So that is what we would like to implement. Vt, the terminal voltage across the panel, should become Vm to achieve MPPT. So therefore, now I have Vt and Vm, these two important variables which we will use here. Now Vm is the reference. We want Vm here to be the reference, and Vt is the feedback signal. So we can sense the terminal voltage across the panel and give it as feedback, and ultimately Vt should become same as Vm. In such a case, when this error is 0, Vt is same as Vm, and in such a case you will see that maximum power is being transferred to the load. So let us say, for example, that Vt is not same as Vm. Let us say Vt is less than Vm. Then error is positive, higher. PI controller will see to is that the output of this increases. Once the output of this increases, there is this duty cycle a pulse width modulation waveform coming in here, because this DC compares with this carrier and gives a duty cycle. Now this duty cycle will change by going from 0 to 1 or 1 to 0 depending upon which type of converter, and appropriately modulate the input resistance seen from the PV panel, which will appropriately position the load line and therefore change the value of Vt. So the value of Vt will keep changing and try to reach Vm such that error here becomes 0. The job of this controller is to always see that the error here becomes 0. If the error here is 0, Vt will be same as Vm, and then you have achieved maximum power point tracking. But how to get Vm? We know how to get Vm because we know this rule. So we will add a block, let us say that is K, and then we will submit as an input VOC. So we provide VOC, gets multiplied, scaled by K, and you have Vm. This becomes the reference. This is your reference section. Vt, which is measured, gets compared with Vm. The error is controlled by this PI controller, and a pulse width modulated signal is provided here, which will modify RT, and the RT will change Vt, and Vt will keep changing till this becomes 0. Under such conditions, when Vt is equal to Vm, error is 0, then you have maximum power point tracking. But here you have only one problem: how to get VOC. We don't have a VOC value, because if you measure this voltage, this is the terminal voltage under loaded condition. How to get the unloaded open circuit value of the voltage across the panel? It will change from panel to panel, it will change from insulation to insulation. Therefore, how to get this value of VOC? Once we have VOC, then we know that the entire control scheme will work. In the neighborhood of this panel, which is delivering power to the load, we will place a small cell called the reference cell, and that reference cell is kept open circuited. There is no load connected across the reference cell. So this cell, which is placed in the neighborhood of the PV panel, wherever this is placed on the rooftop, you place this reference cell also. This is a small cell. The voltage across that is going to give you always open circuit value of this cell, and we will take this cell open circuit value to be same as this cell, provided this cell and this cell have the same make, same datasheet spec. So you choose the reference cell such that it is from the same manufacturer, and then use that to obtain the open circuit voltage. Now this open circuit voltage is given as input to this scaling block, and this scaled value will provide Vm, and this will become the reference for providing making the Vt of this try to reach Vm and thereby achieve maximum power point tracking. So this is the voltage scaling method, reference cell method of maximum power point tracking.